Hi, this is Dan from Earth Science Simplified, and today's lesson is Inside the Earth, Part 1. So we're going to be taking an in-depth look at the Earth's layers and their properties. So let's begin. So there are 5 main layers within the Earth. These are the crust, the upper mantle, the lower mantle, the outer core, and the inner core. And these are separated based on their varying compositions and their varying states. It's worth noting that there's no clear line between the boundaries. These lines are just an approximation, and in reality they're much more transitional, particularly in the area between the outer core and the mantle. This image is good for visualizing a section between the crust and the core. Feel free to screenshot it for revision, and you can see the depth to each layer to the left, followed by the name of the transitional layer, often referred to as a discontinuity, on the right. And you can see you'd have to dig about 6,500 kilometers to reach the Earth's core, where temperatures are about 6,000 degrees Celsius, which ties into the geothermal gradient pictured here. So let's take a look at each individual layer, starting with the crust. The crust is on average 35 kilometers, but obviously varies depending on whether the area is mountainous, etc. And it's only 7 kilometers on average in oceanic regions. It's thinner in the oceanic regions because you have your crust floating on the mantle, and obviously the more dense bit of crust is going to want to sink in further into the mantle. The crust is about 2.7 grams per centimetre cubed, and it's up to 4,000 million years old in areas where there's been little tectonic activity. It's more felsic, so it's richer in aluminium and silica, and if we refer back to our igneous rocks chart from the previous lecture, we'll see that these kind of rocks and minerals are the most common that you'll find in the continental crust. Oceanic crust is about 2.9 grams per centimetre cubed, and it's generally much younger than continental crust. The oldest oceanic crust is generally only 200 million years old, and this is because it's usually subducted and destroyed within that time frame, but more on that in a few lectures' time. So oceanic crust is more mafic, it's richer in iron and magnesium, so continental is more felsic, oceanic is more mafic. And if you look at a typical section through the oceanic crust, often referred to as an ophiolite sequence, you'll see at the base there's peridotite, which is mantle-like material, followed by gabbro, then dolerite dikes, which consist of cooled molten rock that's intruded from the mantle, and the pillow lavas at the top, which is formed due to the dikes erupting at the surface under the water, which means that the lava cools very quickly and forms these pillow-like structures. So again, if we refer to our igneous rocks chart, you can actually see the ophiolite sequence within the ultramafic kind of area. So you'll have your peridotite here, going into your gabbro, then your dolerite, and then your basalt. And you can also see the kind of minerals that we might expect to see in this more mafic oceanic crust. So moving on to the mantle has several sections within it, the 2 main subdivisions being the upper and lower mantle. The upper mantle consists of ultramafic peridotite-like material, and its upper section contains the lithosphere. This is the solid section of the crust and upper mantle that makes up the Earth's tectonic plates. Below that is the asthenosphere, which is classed as rheaed. This is where the rock has been partially melted, so behaves like a solid, but can flow over time. It's this rheaed property that helps drive convection currents within the Earth's mantle. An area within the Earth gives off a higher amount of heat than its surroundings, usually due to radioactive decay, and this then superheats the surrounding area, and as a result, the hot, less dense mantle material rises up, as seen here, before cooling and moving back downwards in a looping pathway. This lateral movement as the material begins to cool acts as a force on the Earth's tectonic plates and causes them to move in the same direction. This is the driving force of plate tectonics, which we'll look into in a few lectures' time. In comparison, the lower mantle is solid, not rheaed. There's no clear boundary between the 2 layers, the upper and lower mantle, as the transition between this rheaed-like material to solid varies by hundreds of kilometers depending on where you are. The lower mantle is made up of stony meteorite-like material, so again is different from the peridotite-like material within the upper mantle, but they're both silicate-based. The outer core is made up of a liquid iron-nickel type material, and the boundary between the lower mantle is very distinct and clear because of the change in state between solid to liquid. And finally, the inner core is still the same iron-nickel material, but it's now solid due to the change in pressure, the increase in pressure as you get closer to the Earth's centre. Okay, so that is it for today's lecture. In our next one, which is Inside the Earth Part 2, we're going to take a closer look at how the varying compositions and states within the Earth's layers affect different things like earthquake waves, etc.